Right. So we were talking about phenotypic plasticity and looking at this experiment done back in 1948 that looks at it. Remember that each plant is genetically identical with the one vertically above or below it. Each plant was grown in the same garden as the plants in a horizontal row. And what makes these plants different from each other is they have different norms of reaction. They respond differently to changes in environment. They all grow shorter when they're grown under harsher conditions. But you can see that, for example, B does very well under low altitude conditions, but does really poorly at high altitude, whereas E doesn't do relatively all that well at low altitude, but does very well at high altitude. So what's different about these 7 wild strains of plant is different norms of reaction. One of the things you have to bear in mind is that heritability isn't actually fixed in a population. There was a 1985 experiment selecting chickens for increased meat production, and narrow sense heritability was practically zero point 0.5. It was 0.47 for the first 4 generations. Then it started slipping. What that reflects is the fact that the more that population was being selected, right, the more selection was being applied, partly just because, some chickens were being removed from the experiment because they didn't make enough meat, and partly because when you do something like that, there's a certain amount of inbreeding that's unavoidable. What was happening was that the population was simply losing variation completely. And if you lose variation, you tend to lose narrow sense heritability, and you lose the ability to improve further. If you have a population like those inbred mice we were talking about Wednesday that is not variable because it's inbred and because it's been strongly selected, heritability can drop simply because there's no variation at all to be acted on. There was a study back in 2002 of German Shepherds, and they scored German Shepherds for behavioral traits. Within the German Shepherd breed, heritability of behavioral traits was very low, between about 0.1 and about 0.25. Now, if low narrow sense heritability means that selection shouldn't work, if we look at all dog species, we know that selection does work because we have artificially selected dogs for various types of behavior. Sheep dogs, for example, have been selected for herding behavior. I had a professor at Berkeley that had a Shetland sheepdog, very smart dog, supposed to be the smartest breed. Shetland sheepdogs begin going insane if you don't give them anything to do. So she would let this dog run around on her front yard, and there were kids in the neighborhood that would come out and play, and the dog would run around herding the kids. As far as I know, that dog had never seen a sheep, but that dog had, behaved in a particular way, and it's something that had been generated by natural selection. For hundreds of years, good sheepdogs get to have lots of babies, and poor sheepdogs don't. We have naturally selected, artificially selected breeds of dogs to be sheepdogs, and we've altered their behavior that way. The same thing for retrievers. Those have been artificially selected to bring back shot birds without chewing them up. They've been artificially selected for soft mouth. Poodles, believe it or not, were bred to be water retrievers. They're working dogs. And the reason why poodles have the clip that they do, the topiary that they've got, is not because it looks foo-foo. It was deliberately made. Their fur is cut that way to give them the maximum mobility swimming through the water, while at the same time having that dense curly fur protecting the vital parts like the chest and the joints. And I've never owned a poodle, but I've been told that full-size poodles are quite happy to jump in the water at any time. They have this behavioral tendency that's been selected for. Poodles that love jumping in water to go, fetch the ducks that you've just shot, they tend to have more babies than poodles that didn't, because poodles that did were more useful to humans than poodles that didn't. So if you look across the spectrum, Newfoundlands, it's the same. They're also water retrievers, and yeah, I am told they will quite happily jump in any water that you give them. So dog breeds have been artificially selected to show different behaviors. So behavior, looking throughout Canis familiaris, the domestic dog, is heritable. It does not have high heritability in the case of German Shepherds, because German Shepherds have been strongly selected and strongly inbred, and German Shepherds don't have very much genetic variability at all, which means that attempts to measure narrow sense heritability are mostly measuring noise. Now, let me see if I can diagram that. I'm going to go to the whiteboard for a moment. All right, let's clear all that. And let me see here. Okay, there's a graph. And on the, this is just, we'll measure some parent's behavioral trait on the x-axis. We don't need to know what it is. And we'll put the offspring behavioral trait on the y. And let me see here. Draw. If we were to measure that behavioral trait for all dogs, we'd end up with something like this. Okay, having a tricky time making all these spots the same size. Okay, so if you measure this trait for all dogs, we might get something like this. And the slope, of course, is going to be close to 1. So we'd have a very high narrow sense heritability. If we have a subpopulation of dogs that has already been very strongly selected, let's say that 4 of these, put it in green, let's say that only those 4 are German Shepherds. Okay, that's a population that has very little variability in the first place, right? Because this is a small circle. They're not very variable. That variation is extremely low. And if we were to take just those 4 points and try to draw a regression line, we might end up with something like this. So for that small subset of dogs, if we measured narrow sense heritability, it would in fact be very low, mostly just because there's very little variation in either the parents or the offspring, and what there is mostly noise. If, on the other hand, we measured narrow sense heritability across a wide spectrum of breeds, we'd find that, in fact, there is a great deal of genetic variance, and it is strongly heritable. So that's the point. Heritability is not meaningful without reference to a particular human population. Um, Heritability can change over the course of selection. Heritability can change depending on when in the life cycle you measure it. And heritability can also vary depending on what subset of the population you're measuring. So just because we say that such and such a trait has 0.5 heritability or something like that, does not mean that that will always be true through all time for all subsets of the population that you measured it in. Heritability is always relative to a particular population. It's not fixed for a given species. So there we have it. A trait can actually have low heritability and yet be inherited genetically. The fact that German Shepherds have low heritability for behaviors simply reflects the fact that A, they're not variable because they've been bred to be standardized, right? Champion German Shepherds have lots of babies like them. German Shepherds that don't measure up don't reproduce. So the breed is pretty inbred, and the breed does not have a lot of variation at all. And yet, if you look at the total variation, the total spectrum of dog breeds, heritability is very high. So heritability is meaningless without reference to the population that you're measuring it in. We also have to be extremely careful about connecting a specific gene to a specific trait. Okay, people have looked at heritability of religion and spirituality. And the heritability of a specific religion, people have tested for this, and it's zero. There is no gene that causes you to become a Baptist rather than a Buddhist. Now, religion does tend to run in families. If your parents were Baptist, you're likely to be a Baptist too. You know, if your parents were Catholic, you're likely to be a Catholic. But that's entirely due to culture, and there's nothing to do with genes. However, psychologists have identified a personality trait that they call self-transcendence. If you score high on self-transcendence, you tend to do things like reading spiritual books a lot, reading whatever your culture calls scripture, meditating or praying a lot, asking religious leaders for guidance in various problems. And that's something you can measure without reference to a particular religion at all. If you're a self-transcendent Buddhist, you're probably going to pray to Jesus a lot. If you're a highly self-transcendent Buddhist, you'll probably meditate a lot. If you're a highly self-transcendent Roman Catholic, you might pray the rosary a lot. But yes, self-transcendence itself is measured independently of the specific religion that you're in. And that is known in typical human populations to have a heritability of about 0.4. Not huge, but it ain't zero. Meaning that we could take a bunch of humans, we could measure their self-transcendence, we'd find they vary. Some people are total God botherers, and some people are complete cement heads who only show up on Christmas and Easter. And most people are kind of sort of in between somewhere. And that variance can be described, and part of that variance is because of genetic variance. So there's a narrow sense heritability of about 0.4. Now in 2004, a guy named Dean Hamer published a book called The God Gene, arguing that he'd found a gene that was responsible for self-transcendence. And it was the gene for a protein called VMAT2. That is a protein that's involved in the release of neurotransmitters. So it makes sense. You have a gene that's involved in brain function. It's involved in releasing neurotransmitters from certain neurons in the brain. Okay, so it's reasonable to think that different alleles of that gene could make your brain work in different ways. Hamer argued that different alleles of VMAT2 were correlated with different degrees of self-transcendence. If you had certain alleles, you were more likely to have high self-transcendence. If you had other alleles, you were less likely to have high self-transcendence. Now, it went published, and the book is kind of a sensational title, The God Gene, How Faith is Hardwired into Our Genes. Ooh, ah. Unfortunately, the book's wrong because faith is not hardwired into our genes. VMAT2 accounts for about 1% of the variance in self-transcendence. Let me show you what that looks like. We'll go back to the whiteboard one more time. Last time for today, I think. So let's say we measured self-transcendence in a population. And over at the left, over here on the left, we've got people who are not very interested in spiritual things at all. You know, we have the cement heads over on the left. Most people are kind of middle of the road. And way over here, we have the God botherers, like that lady in the old Saturday Night Live skits who was praying to Jesus every day that Luke and Laura would get back together on General Hospital. And most of us are kind of somewhere in between. Okay, how do I want to do this? Right. So if we measured all of the people that have some VMAT alleles, we'd get this. Make that blue. There we go. That's the variance in all of the people who have some VMAT allele. If we went and found all of the people that had a different VMAT allele and we measured their self-transcendence, we'd get this. Okay, see what I'm getting at? There's still a very slight difference in means right here, right? Because the mean of one is over here and the mean of the other is right there. So there is a very small difference in the means of populations with these two different alleles. But in the real world case, that difference is only 1% of the total variance. You know, the total variance in the population, you know, might look like, you know, all of this, you know, everybody from the complete cement heads to the, you know, to the frequent flyers, and only a very tiny fraction of the variance in there has anything to do with your VMAT gene. So we do know that self-transcendent behavior has a genetic basis, but attempts to pin it down to any single individual gene so far have failed. We haven't been able to identify a single gene that's responsible, and there probably isn't one. What I'm sure you have is a lot of genes influencing brain function in very subtle ways, working together, probably subject to a great deal of phenotypic plasticity. You know, gene gene function may be modified depending on the action of the environment. Um, so even though we do have some genetic influence on self-transcendent behavior, nobody's been able to pin down a single gene that does all the work. It probably emerges out of the interactions of lots of genes, and there's probably significant environmental effects as well. So let's get back to the bell curve. Remember, this is Herrnstein and Murray arguing that different racial and ethnic groups differ, in particular in average intelligence, and specifically that if you measure IQ for Black and white populations, the Black population is significantly lower, with a bell curve shifted over to the left. Here's what I think's wrong with it. For Murray and Herrnstein's argument to work, four things have to be true. One is that intelligence has to be measurable by a single number. I would argue that single numbers like the IQ might measure aspects of intelligence, but they don't measure everything that we'd want to call intelligence. The second, intelligence has to rank people in linear order. There has to be a way where you can, line people up on the basis of their intelligence from least to most. I would question both 1 and 2, but I'll leave that aside for right now as business for the psychology department, and we can pretend for a moment that IQ is a workable measure of what we're going to define as intelligence. 3, intelligence has to be genetically based. And 4, intelligence has to be effectively unchangeable. As I've said, I'm not convinced that the first premise is true. There's so many subskills and aspects and types of intelligence. I've had psychologists argue that a lot of these separate intelligences are correlated with each other, and there's a measurement that they use that takes all of them into account that they call G. Stephen Jay Gould has been a vocal critic of that, but I'm going to leave that to the folks in the psychology department. And I would consider it an open question at best whether there's any single measurement that captures more than part of what we call intelligence. So 1 and 2 I would regard as dodgy, but I'm not going to argue that right now. We do know that IQ has heritability, and in adults, it can be over 0.85, as much or more than height does. That might look like an argument in favor of Murray and Herrnstein, if intelligence is in fact genetic. But here's what you have to remember is traits can have high heritability and still be profoundly affected by the environment. And here's an example done not with people, but with corn. Over on the left, that is corn growing in a terrific environment for it. It's fertile soil. There's lots of fertilizer. There's irrigation, so there's lots of water. On the left, that's corn that's getting everything it needs to. On the right, you've got corn growing in a drought-stricken field. The plants are a lot shorter. There's less water. The soil is probably more poor. So the corn is not going nearly as well. Now, I am going to go back to the whiteboard just once. Keep this corn in mind. Let's one more time draw a graph. And once again, we'll do, I want to make that black. Let's graph mean corn parental height against mean corn offspring height. Okay, right. So let's say we went out to these fields and we went to the first one and we measured the height of a bunch of corn plants and then we bred them and measured the heights of the offspring that we've got, and we'd end up with something like this. Okay. Within that population, we'd have a very high heritability. And if we measure the slope, it would be pretty close to 1. So where the conditions are really, really good, the slope is about equal to 1, meaning that height is has very high heritability. If the slope's equal to 1, the narrow sense heritability is equal to 1. Okay, so in that population that's growing in perfect soil with lots of water and nutrients and everything, within that population, short corn plants have short offspring and tall corn plants have tall offspring, and narrow sense heritability is very close to 1. Now, if we go to the rotten area, we'd get something like this. And if we measured it there, we'd see something like that. Okay. Within that corn population growing in lousy soil with low water, within that population, short corn plants tend to have short offspring and tall corn plants tend to have tall offspring. So the narrow sense heritability is 1 or very close to it. Now, you might be tempted to say, well, since the narrow sense heritability is near 1, that must mean that the height of corn plants is entirely genetically determined. And there's absolutely no point in trying to improve the environment of our corn plants because it's entirely up to the genes. And you'd be utterly wrong, because you could take those corn plants that are struggling in a lousy environment and, essentially you could take all of, I don't know if I can do this. No, I can't. That's not it. I take all of these. Yeah, you could take all of these corn plants. It's not what I want to do. There we go. And slide them up here simply by the act of providing them with more water and more fertilizer. Okay. In the corn population growing in lousy soil, you have high heritability. In the corn population growing in terrific soil, you have high heritability. But just because a trait has high heritability in a population doesn't mean that the trait is fixed, and it doesn't mean that environment does not play a major role. Traits with high heritability, that's not the same thing as a trait that's genetically determined. Let me go back to, let me, hang on. There we go, back to the slides. So within each population, in each environment, plant height may show high heritability. That doesn't mean that plant height has nothing to do with the environment, that plant height is completely unchanged. The difference between these populations would disappear if the environments were made the same. These plants on the right that are stunted, their offspring would grow much taller if we gave them more water and fertilizer. Mutatis mutandis, you can make the same argument about IQ. IQ does have very high heritability in that in any given population, smart people on average have smart kids, and Less intelligent people on average have less intelligent kids. But high heritability is not the same thing as genetic determinism. Murray and Herrnstein were making the argument that this difference in IQ that has been measured between a European and an African American population is fixed, and there's nothing you can do about it. And therefore, social programs that taxpayers have to pay for, like Head Start and all of that commie stuff, are useless because you're still going to be stuck with a permanent underclass of dark-skinned, stupid people. That's where they are horribly, horribly, horribly wrong. Because just because a trait has high heritability does not make it fixed. It doesn't make it unchangeable. You can do all kinds of wild things. You can change it a great deal if you mess with, hopefully improve, the environment that these populations are growing up in, whether it's corn or whether it's people. To prove the bell curve, you would have to raise a bunch of American babies of European descent and a bunch of American babies of African descent in exactly the same environment. You'd have to do a common garden experiment. The problem is that's not really ethical to do because it would involve taking a lot of babies away from their parents, which normally we don't like doing. The authors of the bell curve simply argue that environmental differences that are big enough to cause that effect are implausible, but they never test it. They simply make the assumption that there's not enough difference in the environment experienced by urban African American kids and urban white kids, but never really look at that at all. That's the gaping hole in their argument right there. And their argument has a lot of its power because they can claim that IQ has a very strong heritability, which means that it's basically programmed into you and there's no way you can alter it, not by your own actions and not by improving the environment for different populations. Those are completely false assertions. And I'm going to go ahead and stop there, but this is why I think the topic is important. It's because arguments like those made in the bell curve are still being made and can still be heard in certain circles, and they're ultimately based on biological misconceptions. They're ultimately based on something that is not the way that genetics actually works.